Can you see my screen? Hello?
Yes, ma'am.
Okay. Okay, so we were looking at patterns and languages that match to pattern, and we left off last class with the following questions. The first is, suppose I give you and a pattern. Can you check whether that string matches to that pattern or not? This is the first question. Second is, if I give you a set of strings or if I give you a language, can you find out a pattern that matches to that language? And we have evidence that for every language we should not be finding a pattern, and we will be later on seeing explicit examples of such languages. Third question is, suppose I give you two patterns. You want to check whether they are equivalent or not, meaning that whether they match to the same language or not. And the last question was, are there any operators that are redundant? We define patterns on sigma dagger, which contains sigma and some other symbols, most of which were operators, plus some bracket symbols. But are there any operators that are actually redundant, that can be expressed using other operators? The meaning can be expressed using other operators. Okay, so this is how we are going to be doing it. First, we will be dealing with this question, whether there are operators that are redundant, and we will look at, then we will be looking at question 1. Question 2, we have some evidence, but for explicit examples we will be deferring it to a later lecture, and we will also be addressing question 3 a little bit. Okay, so are there operators that are redundant? Just from the meaning of it, notice that the symbol epsilon matches to, or rather the pattern, the atomic pattern epsilon matches to the language containing only the empty string. And this would be equivalent to the pattern not of hash at. Okay, not of hash at or null star. Okay, so why? Because let's look at the languages. Language epsilon is L of epsilon is equal to epsilon. Now let's look at not of hash at. What is L of hash at? Can somebody tell me what is L of hash at?
Set of all strings having length greater than equal to 1.
Greater than equal to 1. So basically sigma star minus epsilon. So not of L of not of hash at is equal to, by definition, sigma star minus, or rather, yeah, I can just directly write it from the definition. Sigma star minus sigma star minus epsilon, and this would be equal to just the empty string epsilon. And what about null star? What is, this would be L of null whole star. L of null by definition we know is null itself, the null set itself. So what is null star?
Epsilon. It's a
Right.
containing
Null
only
star is
epsilon.
just the empty string epsilon. So all these things are equivalent. As we saw, just all these three patterns are equivalent. So epsilon in itself can be expressed using other symbols from sigma dagger. Therefore, epsilon is redundant. Similarly, at, L of at is sigma star, and this is also equal to L of hash star, because L of hash star is equal to, by definition, L of hash whole star, which is equal to sigma star. Okay, so again at is redundant. Similarly, the unary plus operator if you write a plus as a pattern, this is equivalent to a concatenate a star. So the unary plus operator is also redundant. Uh, in terms of patterns, redundant in sigma dagger. What about hash? Hash is also not necessary in sigma dagger, because if sigma is a b up to z, let's say, then this would mean that hash is a plus b plus up to z. These two things are equivalent. Replaced hash by these symbols, by this pattern, sub pattern. What about intersection? The symbol that is also replaceable. If I had a sub pattern that read as a intersection b, or maybe alpha intersection beta, this portion can be rewritten as not of a plus not of b, or I mean, instead of a and b, we could also write not of alpha, not of beta. So this can be rewritten, this sub pattern can be rewritten like this, and the same language will be maintained. So the
Ma'am,
symbol intersection is redundant in sigma dagger. Yes?
ma'am, so can we
Yes?
say that epsilon is equivalent to naught of hash plus?
Not of hash plus. Let's see, epsilon equivalent to not of hash plus. Yeah, we can say that.
Okay, ma'am. Okay.
Ma'am, can you explain
Okay.
how is 5 star equal to epsilon?
5 star equal to epsilon, equivalent to epsilon. So this is
5
not
star
phi, this
equals
is
to
null,
epsilon
right?
is- Yes, this is the null set, right? 5.
So if I take null set and I put the asterisk operator, what is that? What is the set result? What is the resulting set?
Empty set starred with itself. Like L of 5
We've
is
learned this in
the
the
empty set,
first
right?
lecture. L of phi is empty set, right? L of phi is empty set. L
L
of
of
phi star by definition
is
is L of phi whole star.
full star.
So phi star. What is this?
This is
Ma'am, 5 to the power 0 is epsilon.
Yes.
Acha, any language to anything to the power 0 is epsilon. Yes, yes. Okay.
Including phi. Phi star is epsilon. This is how it is defined. Recall the first lecture.
Yes, yes, yes. Got
First
it.
or second lecture, yeah. Okay, so the last thing that can be shown to be redundant is this not symbol. In your sigma dagger, this not symbol can also be shown to be redundant, but it's a little bit involved, so we will not see the proof. So what we see is all these things can be shown to be redundant, meaning that you can replace them if it appears in as part of a pattern, you can replace that sub pattern by some, and the same language is maintained. You maintain equivalence. So
Ma'am,
therefore, yes,
ma'am, all symbols cannot be redundant at once, right? They can be independently redundant. Like the not and the other symbol cannot be removed or replaced.
yeah, okay. So this statement, I gave you separate things. So for example, some of them you can remove. For example, you can remove epsilon if you keep not hash and now if you look at only requires hash and star. So at also you can remove after you replace all the epsilons. Similarly, plus you can remove along with epsilon, hash and epsilon, at and plus can be removed together. After you replace epsilon, you replace at, and then and parallelly you can replace this plus symbol. Similarly, hash can be replaced after this. So these things you can replace one after the other. And so this not portion, since you don't proof, it's not clear whether you can replace. So at least these, do you agree that at least the first, except for not everything else can be done sequentially?
Yes, ma'am.
Yeah. So this not, you haven't seen the proof, but once the proof can be seen, you can show that each pattern is equivalent to one which only contains atomic patterns, epsilon, the empty symbol, and operators plus concatenation and star. This is all that. In fact, this epsilon is also not required. All these things you can get rid of. In a sequential manner, you can get rid of this so that your pattern just boils down to symbols, a sequence of symbols only using atomic patterns A from sigma, null symbol, the null set symbol, operators, binary plus, binary concatenation, and unity star. This epsilon we just throw in, the epsilon is just thrown in, this is redundant, but it's just thrown in so that notationally things become simpler. Okay, so it is possible to sequentially get rid of all these symbols. The epsilon we just keep in because of simplicity, and get an equivalent pattern that only where the symbols are only coming from A, epsilon, null set, binary plus, concatenation, and unary asterisk. Just give me 1 minute, sorry. Hello, can you hear me?
Yes, ma'am.
Okay. Okay, so basically the observation is that there are certain symbols in sigma dagger which are redundant, which can be replaced by a combination of other symbols, and still the pattern matches, the entire pattern matches to the same language. So a pattern that only uses the above atomic patterns and operators, where sigma dagger has been reduced to only these symbols, is called a regular expression. So what we can show is that each pattern is equivalent to a regular expression. So any pattern that contains only these symbols, sigma dagger has removed at, unary plus, etc. Such a pattern will be called a regular expression, and it can be shown that since we haven't seen the entire proof of getting rid of not, it can be shown that each pattern is equivalent to a regular expression. Okay. So some notational conventions that we have to follow for patterns, because now we are getting into equivalences and so on. So when we are reading a pattern, if proper bracketing is not there, then you will always give preference to the concat symbol over the union symbol. So if you had alpha plus beta gamma, then, and there were no brackets, then you would read it as alpha plus beta gamma and not as alpha plus beta concatenated with gamma. Notice that these are two different things. Similarly, star is given, the unary operator asterisk is given preference over the binary operators plus or union or concatenation. So if you had alpha plus beta star and didn't have brackets, then you would parse it as alpha plus beta star and not as alpha plus beta whole star. Or you could just simply give proper parentheses. Okay, so now we come to the big revelation that regular expressions are related to regular.
Ma'am, you are
Meant
not
that any
audible.
pattern.
Ma'am, you are not audible.
Ma'am, your voice is breaking.
Ma'am, sometimes your voice breaks.
Can you hear me now?
Yes, ma'am.
Can you see my screen?
Yes, ma'am, but the voice is sometimes breaking.
Yes, ma'am.
Okay, but now is it clear or is it still breaking?
Ma'am, it is comparatively more, but it is still breaking.
Okay, how about now?
Yes, ma'am.
Okay. Okay, so now we are going to be looking at a relation between regular expressions and regular sets. So we saw what were regular expressions. They were patterns where we were restricting the sigma dagger, the symbols in sigma dagger, to be only symbols in A, and the we were also including epsilon for simplicity, the null symbol, and binary plus, binary concatenation, and unary asterisk. The claim is that these three statements are equivalence statements. A set A being a regular set, A being L of alpha for some pattern alpha, and A being L of alpha for a regular expression alpha. So now we haven't seen the proof, but we haven't seen the complete proof, but a pattern alpha can be expressed, is equivalent to a regular expression some alpha dash. Right? So B and C are interchangeable. Now what we have to see is the relation between A and B and C. So we will be first proving, we know that
Ma'am,
by
what is
definition,
regular expression?
I just said it, right? Regular expression is a pattern where every symbol is either atomic pattern A from sigma, null, the null atomic pattern, epsilon
Okay.
atomic pattern, plus operator, yeah,
Yes, ma'am.
plus concatenation, and asterisk. Yeah, okay. So regular expression, just by definition, is a special case of pattern. So this implication is clear. Now we will next show that if A is L of alpha for a pattern alpha, then I can show that L is a regular set. And one way of showing a language is a regular set is by showing that you can construct a finite automata for it. And finally, we'll show that if a finite automata or a finite automata exists for A, or the fact that A is a regular set, I will always be able to provide you with a regular expression alpha such that A matches to alpha. So this is how we will complete the proof of this, proof of equivalence of these statements. So this I will assume just from definition. Now let's go to, yeah, so this I will assume. Now let's go to B implies A, meaning that if A is a language that matches to the pattern alpha, then A is a regular set. So we will sort of go through the inductive definition of a pattern in order to provide a finite automata. So notice that a singleton set A is regular. The set containing the empty string is regular. The empty set is regular. I will not go into the proofs. These are easy to figure out. All of them have finite automata. Now, we have also shown that regular sets are closed under the following binary and unary operators over sets. Intersection, union, not, concatenation, and the asterisk operator, the unary asterisk operator. And we also have closure under the unary plus. We've discussed this. You can figure this out. You have to use epsilon transition, not very difficult. So now we will be inducting on the length of the pattern and trying to show that any pattern will have a corresponding DFA, will have a corresponding finite automata such that the language matching to that pattern is a regular set. Okay, so let's deal with the base cases first. Here are the, in the base case, we will only be looking at the atomic patterns and seeing whether they are regular sets or not. So A, epsilon, null, these are all atomic patterns corresponding to languages that are regular sets. And as we have seen, hash and at are redundant. So we know that wherever hash and at appears, we can replace that with a sub pattern that does not contain hash and at. So we don't need to deal with that. Now we are ready for induction. For any compound pattern, we will induct on the number of operators. So so what are the forms in which the compound pattern can be? The compound pattern can be of the form beta plus, but the plus operator is redundant, so this will not be appearing in, we can assume that this will not be appearing in our pattern. Next is beta plus gamma. This, by definition, L of beta plus gamma is L of beta union L of gamma. Now by induction, beta and gamma are sets which contain less number of operators. Beta and gamma are patterns which contain less number of operators. So these are these correspond, L of beta and L of gamma are regular sets by induction. And since regular sets are closed under union, then L of beta union L of gamma is also a regular set, meaning that L of beta plus gamma is a regular set. Another form is beta intersection gamma. Another form of a compound pattern is beta intersection gamma. So L of beta intersection gamma is equal to L of beta intersection L of gamma. Again, applying induction and the fact that regular sets are closed under intersection, L of beta intersection gamma is also a regular set. Similarly, L of beta concatenated with gamma is a regular set. You can also show the same when the compound pattern is of the form beta star, and also the same when the compound pattern is of the form not of beta. Some of these things are redundant, but just from the definition of regular sets and their closure under different operators, different set operators, you can show that all these things are either redundant or regular sets. Therefore, the language corresponding to any compound pattern is, we have shown that it is also a regular set. Therefore, we are done. We have shown that if A is a if A corresponds to the language matching to a pattern, then it is also a regular set. Any questions so far? Okay. Okay. So before we go into showing that if A is a regular set, then I can construct a pattern or a regular expression such that A matches to the regular expression. Let's look at an example where a regular expression, let's say A B star plus B star A star, this corresponds to a regular set. Let's look at a specific example and let's see how this corresponds to a regular set. So notice that AB star plus B star A concatenated with A whole star can be captured, this entire language, the language corresponding to the language matching to this regular expression can be captured by this DFA as by this DFA as well. This is a DFA. So what are we doing? We have A and then we loop over B and then this A star or this portion is captured by this part of the DFA. Okay, and then you also have B star. You also have another set, which is, so you have basically AB star, AAA whole star plus B star AAA whole star. Now B star A can also be written as AAA whole star plus B star AAA whole star. Notice that AAA whole star is also taken care of in this branch using these edges. B star AAA whole star is taken care of when you start through from this region. Okay, and there is this sync state where anything else that you read that is a certificate that the string does not belong to the language matching to this particular expression comes to this state. Anything else, this is sort of a sync state. I forgot to give a Okay. Somebody had a question?
Yes, ma'am. After AAA star, like from the final state, should we go to the node where the B star is looped, or to the node next to that?
After AAA star, then what are you doing?
Yes, ma'am. In that, the edge shall point to the node where B is looped, or the one it is pointing to.
You want to come from here to here?
Yes, ma'am.
I think you will miss one of the, you will add an extra A. You need
A star will be 3 consecutive A's, and the length will be multiple of 3, right?
Yeah.
Apart from epsilon. So
So
after
isn't this
3
coming
A's,
to a multiple of 4? If you come with an A over here, that will be 4.
okay, ma'am, got it.
Yeah. Okay, so another thing to think about. Yes.
The previous one.
Yes.
After
Yes.
AAA star. Okay.
Yeah.
Yeah. Okay, got it.
Got it? Okay. Okay, so another thing to think about, suppose I asked you for this particular language, A to the N, all strings of the form A to the N, B to the N, where N is greater than equal to 0. So this will be all strings. So what will be contained? You have epsilon, then you have AB, then you have A square, B square, and so on. Right? So can you convert this to a pattern? And also, is this a regular set? Okay, so try to think about whether you can design a DFA or an NFA, or you can construct a pattern. Now that we are sort of trying to prove a theorem that says that a regular set has a regular expression. Try to see whether you can construct a regular expression or a DFA or any finite automata for this particular language. Where are the barriers?
Can
What
you
are the
write
things?
AB star? I mean AB in bracket and then star.
No, this is not the same. I want the same number of A's followed by the same number of B's, not AB star. AB star will be like AB, AB, AB.
Okay, got it.
Yeah.
Can we have 3 nodes with one node looped
No,
over
you
here?
try it. Okay, you try. You think about it. So actually the answer is no. So you think about it. See where the stumbling blocks are. And this will eventually lead to the answer of question 2, which was saying that if I give you a language, can I get a pattern for it? Or can I get a regular expression for it? You try on your own and you see why this is difficult. Where is it that the DFAs that you're trying to construct are failing? Okay, so now we go back to the first question, which says that how will you match a string to a given pattern? So if you give me a string and you give me a pattern, how will you match it? So since I have shown that a pattern, look at the language matching to a pattern, that language is a regular set. What I do is, for that particular language, I construct a DFA. And then I check whether this DFA, I check whether this string is accepted by this DFA or not. And question 3, we will look at which deals with the equivalence of any two expressions, regular expressions or any two patterns. We will look at a little later, but let's complete the proof first, which says that, what is remaining of the proof is A implies C, meaning that if A is a regular set, then A is actually a language matching to a regular expression alpha. Okay, so suppose A is a regular set, and suppose I have an NFA M which is equal to this tuple. So we will define a regular expression that accepts L of M, a regular expression that matches to L of M. Okay, so this is the aim of the proof. If we want to prove this, this is the aim of the proof. For any subset of states X, and take any pairs of states U and V, alpha UVX will be a regular expression that matches to all the strings X that are of the following form. They have a path from U to V with all internal vertices in X, and these paths are labeled by X. As you know, in NFS, this is what happens. So look at all the strings X such that they correspond to paths labeled by X, where the paths start in U and end in V, and all internal vertices belong to X. Now, it is possible that U or V or both of them could belong to X. That is possible. But all internal vertices of these paths belong to X. Alpha X UV, we aim to find a regular expression alpha X UV that matches to all these strings, this set of strings. And notice that if we fulfill this aim, if we can prove this aim, then the implication is that you consider this particular regular expression. If we assume that such alpha X UVs can be constructed for all subsets X and for all states U, V, then you consider this regular expression, summation over all the start states in the NFA and over all the final states in the NFA, alpha SF Q. This would be a regular expression for all strings in LM, and then we will be done. Okay, so is the aim clear? Why we are trying to prove this, and that would be enough to prove this particular statement.
Ma'am, can you please explain the aim again?
Yeah, so the aim is we want to show that for any subset of states and for any pair of states UV, we will be constructing a regular expression alpha UVX such that this regular expression matches to, so L of alpha X UV is equal to all X such that there exists a path labeled by X starting at U, ending at V, and all internal vertices in X. So if I had this pictorially, you look at the NFA, you have this set X could contain U and V, but look at all the paths. There could be these paths could be of any form. There could be many paths. The only condition is all the paths have to start and end at U and V respectively, and all the internal vertices of these paths must lie in X. Consider all these paths. Okay, so they look at the labels of the path. Suppose this is X1, this is X2, suppose this is X1 again. So that means x1 and x2 belong to the should belong to the language of alpha x uv. Clear?
Yes, ma'am.
Okay, and the implication then is, if I can prove this for any subset x and pair of states uv, then look at the regular expression. Look at the regular expression, summation over all start states and over all final states, alpha sfq. This would be a regular expression for all strings that are accepted by M, or all strings in LM. So now it is enough to prove this aim. And we will be doing it by inducting on the size of X. In the base case, X is, let's say, the empty set. There will be two cases, or no, maybe we just have one base case. X is empty set. Now, for the empty set, it is possible that U is not equal to V or U is equal to V. These are the only two ways in which U and V can behave. So suppose U is not equal to V, what can alpha UV empty be? So this will be sum over, look at sigma dash. Sigma dash is the alphabets that are labels on the outgoing edges of U. So you look at U, look at all the outgoing edges, look at the labels on them. This is contained in sigma dash. So if U is not equal to V, then alpha UV empty is going to be sum over all the elements in sigma dash if sigma dash is not empty, meaning that it will be A1 plus A2 plus A3 plus so on. And if sigma dash is empty, then it will just be empty. Okay. Now the next case is, what happens if U is equal to V? This is also possible. Then alpha UV empty is going to be sum over all elements in sigma dash, plus epsilon. Okay. And if sigma dash is empty, then it will just be epsilon itself. So it is U. So it is possible that you have all these edges going outside which are labeled. You could have a labeled loop, etc. And plus you also in this sum over this sigma dash is just all these. Since U is equal to V, it will just be some labeled loops. You have some outgoing edges which is possibly coming back to U itself. All the labeled loops, let's call those. You have certain labeled loops and you have some alpha A1, A2 and so on. So all these alphabets are in sigma dash now. So all these alphabets and plus epsilon, meaning that I have just stayed in U itself. Okay, if I was at U, if I started from U and stayed at U without taking any edges, then at least this, if let's assume that U was a final state, then epsilon at least would be accepted. So that's why this epsilon has been added in if U is equal to V. And if there are no such labeled loops, if sigma dash is empty, then only epsilon, there is a possibility that only epsilon can be accepted if U was an empty, U was a final state. Okay, so this was the base case. Now comes the inductive definition of alpha x uv. Yes?
Ma'am, could you please, ma'am, in the first part of the proof, ma'am, why does it not depend on V anywhere?
Why does it not depend on
V?
Okay, hold on.
Now it should be outgoing edges of U to V.
Right. So this is all the outgoing edges from U to V.
Okay.
And this is also if u is equal to v, then only the loops, the labeled loops at u. It could be a1, a2, and so on. Yeah, sorry, there is a typo here. Outgoing edges of u to v. Because if this is a null set, meaning that there can be no internal edges, you can only directly go from u to v. Okay. This was this was an error. It will be all outgoing edges of u to v. So now we come to defining alpha uv inductively on the size of x. So let's take some q which belongs to x. So let's look at what the paths can be. So basically we will try to consider the paths with respect to q as an internal vertex. So this is x, let's say u and v, and these are all the paths. Now it is possible that some paths do not contain q at all, and there are some paths which contain q. So first let's consider the paths which do not contain q at all. This can be so if they do not contain q at all, let's call them these are the paths corresponding to, these are all the paths that start from u, end at v, and have x as internal vertices. Let's call them p not q union p q, meaning that these are paths that do not contain q as an internal vertex, and these contain q. Now let's consider these paths first. What can the internal vertices be over here for these paths? So p not q, they again start at u, end at v, but internal vertices are in x minus q. They are not taking q, so they take something from x minus q. Now x minus q is a set of smaller size than x, and therefore by induction I should have a regular expression alpha uv x minus q for p not of q, for all the paths for all the strings corresponding to the paths p not of q. Now we come to pq, which contains q. So again we can break this into three parts. First you have any path u to v, any path in pq looks in the following way. It has look at the first occurrence of q on that path, then there could be multiple occurrences of q on that path, and then you after the final occurrence of q, you again have a path from q to v which does not have q. So first occurrence of the path from u to q which does not have q the first path from u to q to the first occurrence of q does not have q, and the path from the last occurrence of q to v does not have q. So then that means and look at all the loops from q to q. Look at the path between the first and second occurrence of q. That will not contain any q. Similarly, from second to third occurrence, that will not contain any q. So let's break this path into, let's say, p1 and then p2, then p3, and so on till pn, if there were n occurrences of q. Pn plus 1, if there were n occurrences of q. So notice that between occurrences of q, I'm not using q as an internal vertex. So in P1, I'm not using any Q as an internal vertex. In P2, I'm not using Q as an internal vertex. So we are breaking each path in PQ into these subpaths where the internal vertices of these subpaths do not contain Q. So that means the set of internal vertices that can be used for each of these subpaths is smaller than X itself. And therefore, we can break this into the regular expression. We know that by induction, we know that there are regular expressions for these sets of subpaths. And therefore, this can be written as alpha UQ X minus Q concatenated with alpha QQ X minus Q star concatenated with alpha QV X minus Q. So we have broken any path belonging to PQ will be a sequence starting from U, then you have some things, then the first occurrence of Q, then second occurrence, third occurrence, and so on. It could be a variable number of occurrences, and then finally the final occurrence, and then V. So we are trying to express each of these parts. We are trying to match each of these parts to one of these regular expressions. Okay, so in between U to Q, there are no appearances of Q. Similarly, from the first and second appearances of Q, and so on. This first part, we are going to be matching to alpha UQ X minus Q. Then from the second to the last occurrence, we will be matching to alpha QQ X minus Q star. And then the final occurrence, we will be matching to alpha QV X minus Q. Okay, so is it clear that this alpha UVX is actually can be expressed as this regular expression alpha UV X minus Q plus alpha UQ X minus Q, alpha QQ X minus Q star, alpha QV X minus Q, which is a regular expression because each of these are regular expressions and we are only taking operations over these regular expressions.
Ma'am, anyway, if the path is considered, means we cannot consider internal vertex as any of the edge means endpoints.
No, that's not true. X can contain U or V. By definition, X can contain U or V.
Okay, ma'am.
Yeah. In general, X can contain U or V. Over here, we are choosing a Q and we are breaking this up in such a way that X does not contain Q. Just for the proof to work. In general, X can contain U and V. We wanted to use the induction. That's why we wanted the size of the set to go smaller, and that's why we broke the path in this form, so that this size we could ensure that this size goes smaller. Because if it goes smaller, we know that by induction there exists a regular expression for those kinds of paths. Fine?
Yes, ma'am.
Okay, so again in words, by induction height, we are inducting on the size of X. The right hand side combines to form a regular expression. Each of these are regular expressions and we are just combining them using the binary plus and concatenation and unary star. So this is going to result in a regular expression again. So we have proved the aim and therefore the implication follows that if you give me a regular set, then I can construct a regular expression for it. And therefore, we are done with the proof of the theorem that says that a set is a regular set if and only if there exists a regular expression for it. So the three statements basically boil down to saying that a set is a regular set if and only if there is a regular expression matching the set. Okay, so let's look at an explicit example. So regular expressions for a DFA that accepts binary strings divisible by 3. So this was the DFA, you had divisible by 3. So this was 0 mod 3, 1 mod 3, and 2 mod 3. And this was the DFA we had constructed. Okay, so if you consider and 0 was the end state, start state, as well as the end state. So you take alpha. So basically the language accepted is alpha 0 0 0 1 2. And this, if I consider 1 over here to be the Q of the previous argument, then this can be rewritten as alpha 0 0 0 2 plus alpha 0 1 0 2 alpha 1 1 0 2 star alpha 1 0 0 2. Okay, and now each of these expressions, please work it out. Alpha 0 0 0 2 will be 0 star, and then this will be 0 star 1. Then this will be 0 1 star 0 1 plus 1 0 star 1, and alpha 1 0 0 2 will be 1 0 star. So this expression turns out to be this very ugly expression if we just put everything together. Okay, so then naturally we come to the third question, that is, can we get a simpler expression? This seems very hard to parse. So is there an equivalent expression that is simpler? So equivalence is a relation that is reflexive, symmetric, and transitive. So if two expressions are equivalent, then one can be substituted for the other. Actually, question 3 is an NP-hard problem. So if you give me if you give me a pattern and ask me for the simplest form, or ask me for a simpler for a shorter pattern that is equivalent to this given input pattern, this is an NP-hard problem. But if you give me specific instances, suppose you give me a particular pattern, then by observation or by understanding, like by applying some simplification rules, we may be able to get we may be able to simplify the pattern or shorten its length. So for example, if I gave you a pattern like 0 plus 0 into 1, then you know that this can be simplified into 0 1, because this 0 plus 0 is not doing much. This is just 0 1 plus 0 1. So this is the same thing, I can write it as 0 1. So these are some observations similar to like algebraic simplification rules. We may use some of such rules. We can construct such rules for patterns as well. And we can say that a particular pattern, we may try to apply the rules on that particular pattern and try to simplify it. So here are some laws of simplification. One is this associative law, that if I have alpha plus beta plus gamma, this will be equivalent to alpha plus beta plus gamma. Similarly, if I have alpha plus beta, this will be equivalent to beta plus alpha. Just check the definition, because look at the union operator. This will be related to the union operator of sets. You check this. Similarly, alpha plus null, this will be equal to null. Again, look at the language, look at the languages corresponding to the left hand side and the right hand side. Alpha plus alpha can be substituted because substituted by alpha, because alpha plus alpha is equivalent to alpha. Alpha concatenated with beta concatenated with gamma is same as alpha concatenated with beta and then concatenated with gamma. So where these brackets are does not matter. Epsilon concatenated with alpha is equivalent to alpha concatenated with epsilon, equivalent to alpha itself. Check the language definitions. Alpha concatenated with beta plus gamma is alpha concatenated with beta plus alpha concatenated with gamma. So so check distributive law over the binary operations on the sets that are matching to the left hand side pattern and the right hand side pattern. Okay, few more. Alpha plus beta gamma is equal to alpha concatenated with gamma plus beta concatenated with gamma. Again, distributive law over the corresponding set operations. Null concatenated with alpha is alpha concatenated with null is equivalent to null. So null, I think you have already seen this. Null acts as an annihilator for any set. So the null set concatenated with any set is equal to that set concatenated with null is equal to null itself. Null acts as an annihilator for this operator. So please check. So these are patterns. So please check whether the corresponding languages are this. Corresponding languages follow this rule. Then epsilon plus alpha concatenated with alpha star is equivalent to alpha star equivalent to epsilon plus alpha star concatenated with alpha. Again, check the corresponding languages. So yes.
And can you explain the second point? Why null concatenated with alpha results
This you
in
have already
null?
seen. I don't have to explain. You have seen this. Check. You recall whatever you've learned in the first lecture or the lecture on strings. You've seen this already. Okay. You recall what you had done. Now we'll introduce a new notation. We'll say alpha is less than equal to beta if the definition of this is the language matching to alpha is a subset of the language matching to beta. Or we can also say that the language matching to alpha plus beta is equal to the language matching to beta itself. If notice that if L of alpha is a subset of L of beta, then L of alpha plus beta is equal to L of beta. Please check this. It's easy to check. Just look at what this L of alpha plus beta means in terms of languages. And therefore, if L of alpha plus beta is equal to L of beta, then that means alpha plus beta is equivalent to beta. So if alpha is less than equal to beta, that basically means alpha plus beta is equivalent to beta. Now, using the languages that are matching to these subsets, set theoretically show that beta plus alpha plus gamma is less than equal to gamma implies that alpha star beta is less than equal to gamma. Beta plus gamma concatenated with alpha is less than equal to gamma implies that beta concatenated with alpha star is less than equal to gamma. You can show this set theoretically. Okay, so these are just some laws of simplification that you can use to simplify a given pattern into something easier to parse. Okay, some other equations. Alpha beta star alpha is equivalent to alpha concatenated with beta alpha star. So please try to argue this for each of the i's. You can argue this inductively on the length of the string. So you can try to see what happens. Can you prove alpha beta to the I alpha is equivalent to alpha beta alpha to the I? Next is alpha star beta star alpha star is equivalent to alpha plus beta star. Again, look at what are the languages on each of the left hand side and right hand side. Combining these two things appropriately, you can get alpha star beta alpha star whole star is equivalent to alpha plus beta star. So try to take alpha star as gamma and try to apply this, or I think you have to apply this first and then you apply this and then you will get this expression. Then epsilon plus alpha whole star is equal to alpha star. You have to apply the second equation in order to get this. Then alpha concatenated with alpha star is equivalent to alpha star concatenated with alpha. So one way of showing it is you know that alpha concatenated with alpha star and alpha star concatenated with alpha. So there are two cases. One is alpha itself is epsilon, in which case it is easy to show. If it's not epsilon, then each of these sides, the left hand side or the right hand side, we look at the languages matching to the left hand side or the language matching to the right hand side. They do not contain epsilon. And then one way of showing is you add the string epsilon to the language on the left hand side and to the language on the right hand side and check whether they are the same or not. Or you can prove it in any other way. So these are certain laws and equations that you can use to simplify a particular pattern or a particular regular expression. So here is an example of simplification. Suppose you are given this pattern, this regular expression. So this does not seem very structural. We cannot, right away, we cannot see any structure of the strings in the language matching to this particular pattern, this particular regular expression. But you will see that if I apply simplification rules appropriately, it will come out to be a pattern. It will come out to be a regular expression where you can easily decipher what are the kinds of strings that are accepted. So the first thing I apply is I write this 1 as epsilon concatenated with 1. And I write this 0 as 0 plus 0. And I get the following expressions. So if I write this 1 as epsilon concatenated with 1, I can take this 1 out as common. And inside I write, I rewrite this expression as epsilon plus 0 plus 0 0 concatenated with 1 whole star. And this 0 I have written twice. I have rewritten this expression with this 0 written twice. Okay, now this can be rewritten as, again, this 0 has been written twice, and this can be rewritten as epsilon plus 0 concatenated with epsilon plus 0 concatenated with 1 whole star, and then this can be rewritten as epsilon plus 0 epsilon plus 0. Okay, so now look at this expression. Lengthwise, it may not be shorter than this, probably it isn't, but structurally, this immediately says that the strings that are matching to this particular regular expression must be those that do not have more than 2 consecutive zeros. Because after every 2 zeros, you will be having a 1. And at the end, you may end with at most 2 zeros. Okay, so simplification can be used. So when I say a pattern is simplified or a regular expression is simplified, it could be both ways. You could be minimizing the length of the pattern, or you could be applying certain simplification rules such that the pattern gives you more idea on the structures, on the structural properties of the strings matching to that pattern.
लानिया तो आइसक्रीम ले आना कल इंडिपेंडेंस डे बन जाएगा.
Can you please mute
Independence Day.
yourself?
Recording.
Okay, any questions? Okay, so we are left with the, let me go back to the questions. Yeah, let me go back to the questions. The first thing is, how hard is it to check if a string matches a given pattern? So how will you do this? The algorithm for this, can you tell me how you want to do it? You're given a string S and you're given a pattern alpha. How will you do this?
Design the automata and then pass S through it.
Okay, so you have alpha, which means that there is an automata. So let's say there is a DFA M, that M such that L of alpha is equal to L of M. And now you have to check if S belongs to L of M. Okay, so the first question is answered. Second question, we have sort of a hint, but what you learn after this is going to make it clearer that if you give me any language, there are languages where you cannot find a pattern or a regular expression matching to that language. For the third question, we cannot always answer whether given an alpha there is an equivalent beta which is or given alpha and beta whether they are equivalent or not, but for certain but we looked at certain simplification rules such that for particular pairs we may be able to show whether they are equivalent or not, or for a particular expression we may be able to simplify it to another one. In whatever sense this simplification is, it could be in terms of the length, it could be in terms of the in terms of understanding what the language matching to this particular pattern is. And we also had a look at what are the operators that are redundant, and in that section we saw that any pattern has an equivalent regular expression, meaning that you can reduce sigma dagger, which is the set of symbols for a pattern, where sigma is the set of input string symbols. You can reduce sigma dagger to only a few atomic patterns and binary and unary operators, while others are all redundant. Okay, so in the next lecture, you will be looking further into how to show whether a language is whether a language has a regular expression or not, and which equivalently means whether a language is a regular set or not. So we still have 45 minutes. So Professor Das, will you be starting the lecture?
Okay, I will do so, but let us just give them some 5 minutes break. After
Okay.
that, I will start.
So
Yeah.
will we resume at 11:15?
Around 15, yeah.
Yes. Okay.
Hello? Am I audible?
Yes, sir.
Yes, sir.
Okay, so let us go to the next section on regular languages. So let me share my screen. Okay, so we have already seen that in order to prove certain language is regular, you have several tools. You may construct a DFA, you may construct an NFA, or you can construct an epsilon NFA. You can write patterns. You can write regular expressions. And currently you do not understand what it means. Later we will cover it in some exercise maybe. So you can also write what is called a linear grammar. So there are several ways for proving regularity of languages. But note that as we started, as we mentioned at the very beginning, is that every such representation of regular languages is a finite representation. Okay, so all these are finite representations. Okay, and therefore we can, by any of this equivalent machinery, whatever you call, address only countably many languages. On the other hand, we have seen that there are uncountably many languages, and the implication is that there must be some languages which are not regular. Okay. So there must be fine. So the question that immediately bugs us is, can we identify some non-regular languages? And can we prove non-regularity? The answer is yes. So there are two tasks: identify such languages and then prove okay. So to this goal, I will first introduce what is called pumping lemma. And once we have some number of, I would say, non-regular languages in our bag, we can do some other kind of arguments to prove non-regularity. But to start with, we must understand what is meant by pumping lemma. Okay. This will essentially prove non-regularity, not regularity. Okay. This is for proving non-regularity only, not for proving otherwise, to prove that certain languages are regular. For that, we will not use pumping lemma. So PL is the pumping lemma. Okay. And it essentially leads to a proof by contradiction. Okay. So what about this lemma? I will give you a formal statement of this lemma a little later, but let me first start with how we are going to use this pumping lemma. Okay. So this idea is something like this. To prove that some language L is not regular. Okay. Then suppose L is regular. And that will eventually lead to a contradiction. Okay. Now, whenever I say L is regular, this will immediately imply L is the language of some DFA D. Okay. And let us assume that D has exactly K states. Okay. Of course, do you agree that finite languages are regular? Languages containing only finitely many strings, are they regular?
Yes, sir.
Right. For example, you can you take each element of that finite set, construct a DFA or NFA or whatever for that, and simply, take all the DFAs together or NFAs together. That will give you an NFA. Okay. So finite languages are always regular. So this is a side note. Therefore, this L has to be infinite. Right? Because I cannot prove finite languages to be non-regular. It's impossible. Okay. So L has to be an infinite language. Then only the question of non-regularity comes. Now, since L is infinite, it contains a string, let us call it W, with length greater than equal to K. Because the total number of strings of length less than K is anyway a finite number. Depends upon the size of the alphabet sigma, but anyway, it's a finite number. So since L is infinite, it must contain a string W whose length is greater than or equal to K. Okay. Now you see that D accepts the string W. Okay, because it is in this language L. Okay, so D accepts W. Okay. So let us say the length of W may be not exactly K. Let's say this is N. This is greater than equal to K. Okay. It is possible that L does not contain a string of length exactly equal to K, but some N greater than equal to K. Okay. So now let us see how this DFA behaves when it reads this W symbol by symbol. And note that this is a DFA, not an NFA. So at every point, there is a unique transition. Okay, so to start with, the DFA starts in the start state. and let us also give it the name P0. And let me write this W as A1, A2, A3, AN, where this each AI is a symbol from the alphabet. Okay. Now, as it reads A1, it will go to a state called P1, which may be same as S, but anyway, I am just calling it P1. Okay. Then it reads A2. It goes to a state P2. It reads A3, goes to a state P3, and so on. Eventually, it reads AN, goes to a state Pn, and it has to be in the set of final states because the DFA accepts the language L. Agree? So now how many states do I have in my list? P0, P1, P2, P3, up to Pn. How many states are there?
N+1.
N+1 states. And by this, n greater than equal to k, this is greater than equal to k+1 states. Okay. So what does it mean? It means that this k plus or this n+1 states, which is at least as big as k+1, cannot be all distinct because the DFA has just k states. So there must be at least one repetition in this list. This is by the pigeonhole principle, right? Agree or not?
Yes, sir.
Okay. If that is the case, let us see what happens. So let us say, go to the next slide. Let us say I have some Pi equal to Pj. We must have for some ij satisfying 0 less than equal to I less than j less than equal to n. Okay. We have to have this. So let us now see the working of the DFA. So you are starting with, let's say, P0, reading certain symbols, which eventually leads you to the state Pi. Okay, and I is less than j. So you once again read some other symbols from the input and end up in Pj, which happens to be the same as Pi. And finally, you read whatever after this Pj, you eventually reach a final state. Okay. So this entire thing is marked or labeled by W. Okay. So I call this part X, this part Y, this part Z. So that means W can be written as X, Y, Z. Also, since I is less than J and we are talking about DFA without epsilon transitions, we must have the length of Y greater than equal to 1. Agree or not?
Yes, sir.
Okay, good. So now suppose that, consider this string. So for a reason, I will call it W1. For a reason that will be clear very soon. Now suppose I am considering this string W naught. This is the same as this with the Y part removed. Then what will happen? The DFA will start from the same start state. It will come to PI. But PI is same as PJ. So even if it does not read the intermediate substring Y, it will stay in this same state. Then it reads Z and eventually reaches the final state Pn. Agree or not? In other words, this will be in L as well. Happy?
Yes, sir.
Okay. Now consider this string W2 xy squared set. So what will happen? The machine will go from state P0 to Pi upon reading this first x. Then it will go to Y. It will go to state Pj. Okay, which is the same as Pi after reading this first Y. Okay, so this is nothing but x, y, y, z. Now it encounters an extra y, but this state and this state are the same. Therefore, after reading the second y, it is just a kind of, I would say, completing a cycle, starting from Pi, ending at Pi. Okay. After these two y's are read, so once again, another y comes, it reads here. Okay. Then it encounters the final substring z. It will eventually end up in Pn, which is the final state. So W2 is also in L. Any confusion? I think no. So I can simply generalize this concept and I can say that Wi, which is x y power I, z, is in L for all I greater than equal to 0. Happy?
Yes, sir.
Okay. So what we are doing here, given this XYZ, this is a case of what is called pumping out. You pump out Y from XYZ. But this pumping out can be done only once because there is only one occurrence of Y. And here for I greater than equal to 2, you are essentially pumping in. Okay. That is why this is going to be called the pumping lemma. Pumping out one occurrence of Y you can pump out, and you can pump in as many occurrences of Y as you want. Okay. Now, by pumping in and out, or by doing, either pumping out or by pumping in, we will produce some Wi, maybe W0, that will not fit the description of L. Okay. So, by pumping in or out, we will arrive at some Wi which cannot belong to L. Okay. That will eventually produce the desired contradiction. So this is a typical pumping lemma proof. Okay. So I will give you an example to illustrate on a very specific language. Okay. Which actually SK has already talked about, the language A power n, B power n. So this is one of our first languages to prove non-regularity. Okay, so this is the example, first example. Okay, says that the language A power n, B power n, such that n is greater than or equal to 0 is not regular. So this consists of strings of the form epsilon, AB, AABB, triple A, triple B, and so on. Okay. So it's not AB whole power n, as somebody pointed, I'm told today. Okay. So intuitively, I am soon going to apply the pumping lemma on this language. But before doing that, let us have some intuition. Okay. So some number of A's are coming, and then some number of B's are coming. Okay. This count and this count have to be matched. They have to be equal, right? So what kind of memory does a DFA or an NFA has or have? It can remember certain things in its states. Yes or no? It has no external memory. All it can remember is by using its states. Okay. And the number of states in any DFA is finite. Therefore, very large counts like this n cannot be remembered using the states alone. Do you agree with me? N can be very large. Okay. But using only finitely many states, you cannot simply remember how many n's have come, and then later you verify that the same number of b's have come. So this is an intuitive justification why this is not going to be regular. Okay. You need some external memory to store this n in some fashion. Okay. And when we study context-free languages, we'll use a stack to remember this n and then verify that this exactly the same number of b's come. Okay. But this is still an intuitive understanding. This is still not a proof that this is not regular. So for a formal proof, I need the pumping lemma. Okay. So once again, I start with, let us call it L. Suppose L is regular, but then I have a DFA accepting L, and K is the number of states. In D. Okay. So I have to produce a string N and string W of length at least K. So I can take this string. So this is my W. Okay. And its length is this. plus this, which is greater than or equal to k. Okay, if k is odd, definitely n is bigger than k. When if I cannot produce a string of length exactly equal to k if k is odd. If it is even, it is fine. Ceiling of k by 2 is exactly the same as k by 2. Okay. So by the argument that I have earlier explained, the length of this W is greater than or equal to k, and therefore I have a situation like W can be decomposed into 3 parts, X, Y, Z, with Y, length of Y greater than 0 or greater than or equal to 1, and for all I greater than or equal to 0, is in L. Agree?
Yes, sir.
Okay. So we have to have some such X, Y, Z, some such decomposition. Okay. Now I will consider, so I have this A, ceiling of k by 2, this many A's. I also have this B, exactly equal number of B's. Now, there are 3 possibilities. Y is completely inside the block of A's. So this is case 1. Y is, so case 1. Case 2 is this. Y is completely inside the block of B's. And the third possibility is that Y spans across the AB boundary. So there are no other possibilities, right? Okay. So in case 1, you look at, let's say, W0. So let's say the length of Y is L, greater than or equal to 1. So what will be XZ?
A to the power ceiling of k by 2 minus L be your ceiling of k by 2.
Okay. And this belongs to L. Obviously a contradiction because L is greater than or equal to 1. You can also look at W2, which is XY squared Z. And this is ceiling of k by 2 plus L, the ceiling of k by 2. This is also in L. This is absurd, right? We are starting with a power n, b power n. These 2 counts must match. And now I have produced a string, which is certainly not in L. Okay. Likewise, if I look at case 2, W0 will be XZ, which is The count of A will remain the same, but the count of B's will strictly reduce. And this will still be accepted by our DFA. Again, a contradiction. Likewise, you can look at W2, which has excess B's. Okay. And still it has to be in the language L. Okay. Now, if I look at case 3, okay, so I have something like this, A. And Y is basically straddling both the blocks. Okay. And I do not have any control on how far it goes here or goes here. Okay. So let's say in this case, I have something like this. Y is some A power, what symbol shall I use? R. No, R is, okay, R is fine. And B power, S is the start state, so let me use T. Okay. So for some R and T greater than equal to 1. Okay. So if I now look at W0, XZ, what will be it? Tell me.
A power ceiling of k by 2 minus R, B power ceiling of k by 2 minus B.
Good. Minus T. Okay. But it is very much possible that R is equal to T. Nothing prevents from this to happen, right? Okay. So if R is equal to T, no contradiction. Okay, I have no control over R and T. Is it clear? It depends upon how the DFA behaves, how the hypothetical DFA behaves. It may give R equal to T, and then I arrive at no contradiction. Okay.
Yes, sir.
Okay, so if I now look at W2 x y squared z, what will be it?
A power k by 2 plus R, B power k by 2 plus T.
No, sir. After B power T, there will be A power R, B power T.
Okay, so what will be it? K by 2. You are introducing another. So it's something like this. A, okay, something. K by 2 minus R. Then you are having A power R, B power T. Another occurrence of A power R, B power T. This is followed by K by 2 minus T. Okay. So can you see a contradiction now?
Yes, sir.
This. And A appears after a B. So this string is not of the form A power n, B power n. Okay. Or for that matter, not of the form A star, B star. Okay, because there is an A appearing after a B. Okay, so in all these cases, these are only three possibilities. I could arrive at a string W0 or W2, which certainly does not fit the description of L, So if a hypothetical DFA like D did exist, then the language accepted by D cannot be equal to that language A power n, B power n. So this contradiction eventually proves that the language A power n, B power n is not regular. Any query?
Sir, I have one doubt.
Yeah, tell.
Sir, in the like proof of pumping level, like where you mentioned how we prove, like there you stated that we will show that not all strings of x, y power I, z do not belong to the regular set. So means that is a trial error based method, like we will check manually for some strings and then find a contradiction for different cases, or there is some like concrete step-by-step
Yes,
process.
yes. Like every other theorem, this is like you have to have some kind of I would say foresight. Which string you are going to take, how you are arriving at a contradiction, and we will see several examples to illustrate. Okay. Yes. Okay. So what W start with? This is definitely your, I would say, foresight. Yeah. So any other question? Okay, so if not, I will tell you in another 5 minutes a simplification of this proof. Simple. So if I started with the string a power k, b power k, this is of length 2k, which is definitely greater than equal to k, right? And then if I look at the behavior of the DFA on this a power k, b power k, so this is my a power k, this is my b power k, sorry. Then if I restrict my attention only to this part, which is of length k, the repetition will happen here with absolute certainty. Yes or no?
Yes, sir.
Okay, so this is okay. This but I mean, wherever the machine stays here, that is not necessarily a final state. But anyway, it is anyway after that it is going to read b power k and reaching a final state. Okay. Now, since the repetition will happen here with absolute certainty, there is only one possibility for y. What is that?
E.
Some a power something, right? Some a power r for some r greater than equal to 1. And what does it imply? How does it simplify the proof? You now only consider case 1. There is no need to consider case 2 and case 3. In or out, there will be either a surplus of S, there will be a deficit of S. So now case 1 suffices. Happy?
Yes, sir.
Okay. In fact, this simplification suggests if I feed to that hypothetical DFA any string of this form, I have not used good symbols. Okay, W. Okay, any string of the form U, W, V, such that the length of V is greater than or equal to the number of states. Then we'll have a repetition here. And I can still put a repetition in V itself. It does not matter. This is the start state. Here I have a final state. And if I have sufficiently many symbols in any part, okay, then a repetition is bound to happen in that sufficiently long part. Exactly the same proof, right? Okay, so with this understanding, I am going to stop here. I will give you a formal statement. I will have to revise this little. All this X, Y, Z, and this I can break as VW. I think that is the notation our uses. Okay, so let us start afresh in the next week. Where I will continue with this pumping lemma and with many other examples. And if time permits, we will start a new topic called minimization of DFA. Okay. And unlike regular expressions, this minimization problem for DFA can be very easily solved. So let us stop. It's just going to be 12. Okay. So if you have any immediate questions, let me know. No? Okay, then let us stop.
Thank you, sir.
Okay, bye.
Thank you,
See
sir.
you on Thursday.